Hello everyone, today let's take a look at Quantipose number 3, another question we're going to solve using symmetry. So we have two gamblers playing a simple coin toss game. Gambler A has n+1 fair coins and gambler B has n fair coins. So what is the probability that A will have more heads than B if both of them flip all of their coins? So this would be really hard to solve if you're not using symmetry. It would basically require the sum of a bunch of sums of different binomials. So the fact that you can solve this so easily with symmetry is kind of cool. So where does the symmetry come in? Well, gambler A has n+1 fair coins and gambler B has n fair coins, so there will be symmetry through the first n flips. So for the first n flips, let's define some random variables. Let's let A be the number of heads for gambler A, and let's let B be the number of heads for gambler B. So since these are both samples from the exact same distribution, we have symmetry. What does that mean? Well, that means the probability of A being greater than B is just equal to the probability that B is greater than A. So obviously for the first n flips, we only have three total outcomes, and that is A greater than B greater than A, or B equal to A. So obviously the sum of the probabilities of these outcomes is just going to be equal to 1. They completely partition our sample space. So if we come down here, I'll draw a little diagram. This is a diagram of the sample space through n flips, and I tried to draw it such that the probability mass of A having more heads is equal to the probability mass of B having more heads. And collectively, they make up the entirety of this box, which represents the sample space. But now this is for the first n flips, and A has n+1 coins. So A has one more flip, right? Okay, so law of total probability. We have events here that partition our sample space. We have one more coin flip to go. So what's the probability that A wins after his coin flip, given that he arrived there in each of these situations? So again, just law of total probability, the probability that A wins is the probability that A wins in each of these situations, weighted by the probability mass that it takes up. We've already proved this, we've already shown this. All right, so first of all, what's the probability that A wins, given that A has more heads through the first n flips? Let's just say that A has 50 heads and B has 49 through the first n, and then A has one more flip. So what's the probability that he wins? Well, he's always going to win, right? Even if he gets a tails, he's still going to have more heads than B because he started off that way. So the probability that A wins, given that A has more heads through the first n flips, is 100%. So it's going to occupy all 100% of this probability mass. So now, what if instead, through the first n flips, B has more heads than A? So for instance, what if B has 50 heads and A has 49? Well, A has one more flip to go, but notice that even if he gets heads, he's at best going to be tied with B, and in a tie, B wins. So the probability that A wins, given that B has more heads than A through the first n flips, is 0, right? This is going to be 0 here. This here was 100%. Now we have one situation left, right? What's the probability that A wins, given that A is equal to B? So for instance, A and B both could have got 23 heads, let's say. So A has one more flip. So notice that if he gets a heads, he will win because he will have more heads than B, right? He'd go to 24 and B would have 23. But if he gets a tails, well, then they would still have equal, and that means that A loses. So what are A's odds of flipping a heads? Well, obviously it's going to be 50%, right? 1/2. So when A has the same number of heads as B through the first n flips, he's going to win 50% of the time. All right, so this right here was equal to 1/2. So what is the probability that A wins? Well, if you notice something interesting up here, the red region, which was the probability that A wins, takes up 50% of our total probability space. So how do we know that? Well, remember we had symmetry where the probability of A being greater than B was equal to the probability of B being greater than A. So if we just look in this blue box, A wins half the time, right? And then notice that in the remainder, right, 1 minus the probability of being in that blue box, A also wins half the time. So we know that the probability mass of the blue box plus the probability mass of the orange box sum to 1, even if we don't know specifically what they are. And we also know that the red region, right, representing where A wins, takes up half of both of these. So therefore, the probability that A wins in general is just 1/2, right? Because it's like saying, oh, I'm taking 1/2 of some value x plus 1/2 of some value y, and I know that x plus y is equal to 1. Well, then I can just pull the 1/2 out, and then I have x plus y here, and we know that this is 1, so we just get 1/2. If you wanted to solve this actually using the equation and not just visualizing it, well, let's just draw out what this is. Well, it's going to be equal to, well, we got 1 here, so just the probability of A being greater than B. We got a 0 over here, so that term's going to go away, and we got a 1/2 times the probability of A equals B over here. Now the thing is, even though we don't know exactly what these terms are because they'd be really hard to solve for, what we do know is the probability that A is greater than B is 1/2 of some value such that when it's combined with the probability that B equals A, well then it sums up to 1. So basically we're saying that this value here is equal to 1/2 times 1 minus the probability that B equals A. And then it's easy to see once we add this term onto this and then we distribute this 1/2, these are going to cancel out and we're just going to be left with 1/2 as well. So that's how you can get it using the formulas, right? So again, we use symmetry again here to make a really hard question a lot easier, and we use the law of total probability when we got to here. So yeah, this is just a good problem that ties a lot of things together.